Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, dear students. Welcome back once again to the TV learning programs. I'm teacher Patrick, as usual, and I'm so privileged once again to be with the Senior 6 chemistry class. You remember in the previous lessons, we've been talking about the benzene and its derivatives. Still, we are on Unit 5, which is benzene and its derivatives. And we have so far gone to Lesson 8, which is chemical properties of the benzoic acid and some uses that we'll be able to look at in our lesson for today. By the end of this lesson, dear students, I hope you are ready to go. You will be able to state and explain some uses and some physical properties of benzoic acid. We are using benzoic acid simply because this is the simplest member of the aromatic carboxylic acids. And two, you'll be able to describe and categorize some chemical properties of the benzoic acid. So before we continue to look at some of the physical properties and the uses and the chemical properties, I would like us to first freshen up by reminding ourselves about what we talked about in the previous unit. We talked about the nomenclature, we talked about the preparation methods, if you remember, and then we mentioned the acidity of these carboxylic acids. So I just want us, as we freshen up, I just want to remind you about the acidity. No, maybe we'll not go through again to the properties and the nomenclature and the preparation methods. But I want us to briefly talk about the acidity of the carboxylic acid. This is benzoic acid, and I want us to compare this with the ethanoic acid. Which one of these is a stronger acid, and why? I hope we talked about this before. If you remember, with the ethanoic acid. So let's look at this again. So when this benzoic acid, which can be simplified as COH, so in presence of water, so it will ionize partially. They are all weak acids, but one is more stronger than the other. So we'll have C6H5COH, then plus the hydroxonium ions being produced. Or we can present this in this form, COH, partially ionizing C6H5COR minus plus the hydrogen ions. These hydrogen ions are the same as that. So the hydrogen ions that are produced in water, that are released in water, make these compounds acidic. So the ethanoic acid also behaves in that form. COOH, so in water, in solution form, so it will form CH3, COO negative, plus the hydrogen ion. So it behaves in the same form. The ionization is the same. But benzoic acid, remember, we are comparing the strength of the acidity between benzoic acid and this ethanoic acid. This ethanoic acid is a weaker acid. Why? Why is it a weaker acid compared to this? So when this benzo, the ethanoate ions, with the oxygen, the negative charge, so you remember this is the resonance structure for this compound. So this one can be written in this form. So they are the same. Or this can be written in this form where you have the oxygen here with the negative charge. These are dotted arrows. So this negative charge, this methyl group, has positive inductive effect. So it donates the electrons towards this carbon. And therefore, it localizes the positive charge. So it stabilizes the negative charge on this carbon. And that makes it less acidic. Whereas in the benzoic acid, these benzoate ions, when we talk about the benzoate ions, you have this compound over here. So this is the benzoate ion here. So the negative charge over here is delocalized, so it enters within the ring, so of the benzene, and that stabilizes. So the movement of the negative charge, because of the overlap of the orbitals, this negative charge enters within enters the benzene ring, and therefore stabilizes the negative charge and makes it more acidic. So benzoic acid is a stronger acid. Benzoic acid is a stronger acid compared to ethanoic acid. So in general, aromatic acids are more stronger than aliphatic acids. And we talked about the effect of the substituents on the acidity. So we are not going to repeat all those. So let's go straight to state some of the physical properties. So these aromatic acids are crystalline solids. They exist as crystalline solids because of the high molecular mass and therefore high, strong van der Waals forces, strong intermolecular forces. So that's why they exist as crystalline solids. They have high melting points compared to this explains still the reason is still on the strong intermolecular forces. The molecular mass, when you look at the molecular mass of this one and this, it is much higher. And they are slightly soluble. So compared to the aliphatic carboxylic acids, the carboxylic acids are more soluble because they form strong hydrogen bonding compared to aromatic carboxylic acids. Why? Because the benzene ring outweighs the hydrogen bonding that is formed. It forms the hydrogen bonding. I just want to clarify this. It forms the hydrogen bonding much as well as the aliphatic carboxylic acids. But the hydrogen bonding in carboxylic acids is reduced by the big size of the aromatic group, which is the non-polar part of the aromatic carboxylic acids. So as we said earlier, when we talk about this, the acidity, it will depend, because we said carboxylic acids with unsubstituted benzene ring are slightly stronger acids than aliphatic acids, as I've mentioned before. But it also depends on the substituent that may be attached on that group. So for the most part, the reactions of carboxylic acids are identical to those ones of aliphatic carboxylic acids. So the reactions are identical. I mean, the reactions of aromatic carboxylic acid, they are identical to those of the aliphatic carboxylic acids. The difference is only on the rate, the speed at which these reactions take place. Compared to the phenol, the acidity, these carboxylic acids are stronger they are strong acids compared to the phenol. We mentioned that one slightly back in the previous lesson when we were talking about the phenol compounds. So some of the reactions that we talk about, the side chain reactions, these are the reactions similar to those of aliphatic acids, and they are similar even to those of acids, reacting as an acid. Carboxylic acid, this is benzoic acid in water. So all acids ionize in water. So this behavior is shared throughout all the acids. The reaction with water, the ionization characteristics, and the reaction with sodium hydroxide. This is almost sodium hydroxide forming the salt and water. Reaction with carbonates, the salt, carbon dioxide, and water, and the reaction either with metals or sodium hydrogen carbonate. These are the reactions which are shared throughout all the acids. All the acids share the same reaction with water, with sodium hydroxide, that is a neutralization reaction. With sodium carbonate or sodium hydrogen carbonate, liberating carbon dioxide. You remember when I was talking about the phenol, I said phenol does not react with, because it is a very weak acid, it does not liberate carbon dioxide when it reacts with sodium carbonate and sodium hydrogen carbonate. So these reagents, either sodium carbonate or sodium hydrogen carbonate, they can be used to distinguish between phenol and any other carboxylic acid. So the reaction with water, once again, so this is the reaction. All acids, for example, if you have an acid, any other acid, you may talk about either hydrochloric acid reacting with zinc. This will give zinc chloride plus the hydrogen gas. So all acids. So we will talk about this sulfuric acid with the sodium metal. This will give sodium sulfate plus the hydrogen gas. So all the acids behave. And this is the characteristic of all acids that we are talking about. So in this case, when we're talking about the side chain reactions, we are referring to the behavior of these aromatic acids, compared to the mineral acids, because the reactions are all the same. The esterification, this is not the first time that we look at the esterification, remember, with aliphatic carboxylic acids. For example, if you have ethanoic acid and react it with an alcohol, CH3, CH2, OH, in presence of the acid and heat, you remember talking about this reaction. So we are going to get an ester, we're going to get an ester and water. So this is an esterification, similar to the aromatic carboxylic acids. I talked about I had even talked about the mechanism. I discussed the mechanism when I was talking about the alcohols. So you can just refer to that video and look at so when the carboxylic acids, so this is esterification. So this forms ethyl benzoate. So we have benzoic acid reacting with ethanol in presence of hydrogen ions, forming ethyl benzoate. So the reaction is similar. As I said, the reactions are similar to those ones of aliphatic carboxylic acids. So acid halides, the same reaction with cyanide chloride, with phosphorus chloride. So if you have, for example, I'll just use the reference of the aliphatic carboxylic acids because I said these reactions are the same. So if you have, for example, this is ethanoic acid, now combining with sulfur dichloride oxide, so it will form ethanoyl chloride plus this will give sulfur dioxide plus hydrogen chloride. So the mechanism for this reaction, for example, let me discuss the mechanism. How does this reaction take place? So I had discussed this mechanism with the alcohols. We had seen this alcohol. So this is ethanoyl chloride. So you see when it reacts with phosphorus 5 chloride, and or sulfur dichloride oxide or thionyl chloride, then it gives those are acid halides. So the mechanism here, you'll have CH3COO, so you can have OH. This is double bond, the oxygen. Then you have the sulfur, chlorine. This is chlorine. So the chlorine is more electronegative. So if it is more electronegative, it means, what does it mean? That this chlorine is pulling the electrons towards itself. And as it pulls the electron, then this one forms a partial positive charge. And the electrons within here, there is high electron density, so they will attack that sulfur with a positive charge. And therefore, this will form CH3CO. This is H. You'll have COS with one chlorine. Remember, another chlorine has been removed. So we have only one chlorine. So what happens in this case? So this bond, this chlorine has to move as this one comes to replace. Because as this chlorine, once again, the same process happens. This chlorine is moving away because it is more electronegative. So there is rearrangement of the bond. So this forms CH3, C, oxygen. The hydrogen has been removed, so you'll have this one forming a positive charge. So the chloride with the negative charge, such that is a nucleophile. So this one will attack, and then it forms CH3, CO, chlorine, then plus sulfur dioxide, which has been formed. The chlorine that has been formed there with the hydrogen, because this hydrogen has been removed, then will form the hydrogen chloride as the gas. So the same mechanism also takes place. So if you have the benzoic acid, it is reacting with phosphorus chloride and the same reaction, thionyl chloride, which is formed. So if you have also phosphorus 5, so instead of using, because here I'm just comparing the reactions. I said they are the same reactions. So if I'm not using ethanoic acid, that means I'm replacing ethanoic acid with benzoic acid. So the reaction takes place. These are side chain reactions. So it is taking place on this carboxylic acid. So the same thing happens over there with the benzoic acid. So if you are talking about the phosphorus 5 chloride, that's an example. C6, let me use benzoic acid. The hydrogen, you have the double bond, then you have the phosphorus 5 chloride. So there are 5 chlorides, 1, 2, 3, 4, and 5. So one of them, so each of these chlorides are pulling the electrons towards themselves. So if they are pulling the electrons towards themselves, what happens? If this one is moving because of the electronegative, high inductive, the negative inductive effect, so the same happens. So you'll have C6H5C. Oh, this one had hydrogen, remember? So this is oxygen with the hydrogen. So this is oxygen that has been, because one of the bonds have been removed. So you'll have P4 because one chlorine has been removed, has broken away. So that is the compound that is formed. So what happens? Here you'll have C6H5C or H, you have oxygen with P3, one chlorine minus. So this one is removed. Therefore, the bond rearrangement forming that. So meaning you will have this compound C6H5C, or this is the double bond because there has been rearrangement. This one forms a positive charge. Then plus PO3 chloride, there is a chloride that has been formed. So this chloride here is a nucleophile. So this nucleophile comes right away and attacks this positive charge. So this it forms benzoyl chloride. C6H5CO chlorine. This is benzoyl chloride with this compound has been formed and then the hydrogen chloride that is being formed. So this is slightly different reaction because aliphatic carboxylic acids react with strong reducing agents. When they react with strong reducing agents, they are reduced to alcohols in presence of ether. So this reaction is similar to other carboxylic acids that we have mentioned. If you have ethanoic acid in presence of strong reducing agent, that lithium aluminum hydride in ether, that is ethoxyethane is an ether, then it will be reduced to ethanol. So this benzoic acid in presence of lithium aluminum hydride will also be reduced to methyl, that is benzyl ethanol that is formed over there. So that is the reaction. Another reaction which is different, which is also reduction reaction. If the reducing agents are not strong enough, if they are not strong enough, there will be destruction of the benzene ring. So here we are talking about this. You see what happens over here. So this, instead, we are looking at the reaction taking place over here on the side chain. But using hydrogen or sodium in alcohol, the reaction now destroys the benzene ring. It doesn't take place. So strong reducing agents are the only ones that reduce aromatic carboxylic acids to alcohol. If the reducing agent is weak, then it reduces it. The benzene ring is reduced to an alkane, or a cyclic alkane. So that is the difference between the reduction methods of these carboxylic acids. I repeat, in presence of strong reducing agents, carboxylic acids which are aromatic behave in the same way as aliphatic carboxylic acids. They are reduced to alcohols. But in the case the reducing agent is weak, I've just given an example of the hydrogen or sodium in alcohol. The reducing agent won't be able to reduce the carboxylic group to an alcohol. Instead, it will destroy the benzene ring as it is indicated over there on the screen. So reaction with ammonium forms the amides. So that reaction, that is the reaction still that we looked at in the, it is shared between aliphatic carboxylic acids and aromatic carboxylic acids. When you have a carboxylic acid, for example, CH3, I'm just comparing this with ammonia in presence of heat. So this will give CH3, CONH2, then plus water. This is an amide. This is an amide, and therefore, if we replace this ethanoic acid with benzoic acid, that is C6H5COH plus the ammonia, this will give C6H5CONH2, then plus water. So this will also be an amide that is formed. So there are reactions which are shared, which are similar. The mechanism are similar as well. So let's look at the mechanism for that reaction. So what happens, the nitrogen here with the electron rich, with a lot of the lone pairs, will attack the carbon containing the oxygen. So this, in this form, CH5CO with OH. So this oxygen being more electronegative will be moving. So I said the nitrogen with electron-rich, which behaves as a nucleophile, now will attack this carbon that acquires the positive charge. And therefore, what forms here is C6H5, oxygen with a negative charge. There is another oxygen, so you have nitrogen, which has acquired a positive charge. So in that, the next step, we have what we call the proton shift. The proton shift or rearrangement of the electron. So this electron now comes here. So one of the electrons break, and then you have C6H5, CO negative charge, O2, this becomes NH2. So this one moves away as there is rearrangement of the bond, and then you form C6H5, C oxygen with NH2, then plus the water, because the water has been eliminated. That is the amide. That is the simple mechanism. Then there are substitution reactions. There's reactions on the ring. So for this one, you need to remember that a carboxylic group is electron withdrawing group. It removes the electron within the ring. And therefore, if you remember the effect of these substituents, position number 2, position number 3, and position number 5, the meta positions, electron withdrawing groups direct other substituents to position number 3 and position number 5. Those are meta positions. So you should remember that. So some uses in medicine, dye industry, making aniline brew, that is also a dye that is also used in industry. Because of the stability, used as a preservative, benzoic acid. So before I leave, I just want to leave some homework, and there is only one question. It is saying, one of the products from vigorous hydrolysis of oil of bitter almonds is a mandelic acid. That is not the real name of this mandelic acid. It can be synthesized from benzaldehyde in 2 steps. So there is that is benzanal, step number 1, forming J, step number 2, and then forming that 2-hydroxy, that is the compound they are calling mandelic acid. Suggest reagents and conditions for step 1 and 2, and draw the structural formula of the intermediate J. B, suggest the structural formulae for the products of the reaction of mandelic acid with the following reagents. We have hydrogen bromide, phosphorus 5 chloride, we have ethanoyl chloride, we have ethanol and hydrogen chloride and hydrogen in presence of acid, and then finally sodium hydroxide. That's the question. I hope you have captured the question. I thank you so much for being with me in this lesson. I hope we will meet in the next lesson. Bye-bye.